So I'm going to be talking about, well, I think the title there was Big Data and High-Dimensional Statistics. So I guess that's sort of a rough title, but more specifically I'm going to be talking about large-scale regression with sparse data. Okay, so first of all I'm going to talk about large-scale regression and what we mean when we talk about large-scale regression. And I'll talk about this in relation to maybe the more familiar context of high-dimensional regression. Now, b-bit min-wise hashing here, which I've mentioned, is a technique for performing large-scale regression. And the interesting thing about this is it's a totally bizarre technique. I'll describe it in this talk, and you'll see that it really appears to make no sense whatsoever. So this work that we've done here is to, well, try and get a theoretical understanding for this technique. And in arriving at this theoretical understanding, we found a few sort of methodological improvements as well. So I'll describe the theoretical results, and I'll finish with some numerical examples. Okay, so what is high-dimensional regression? In high-dimensional data is where we have many variables and maybe not so many observations. And the typical example which everyone quotes for high-dimensional data is microarray data. And there your observations might be tissue samples or patients. You might just have a couple of hundred of them. And your variables are genes or expression values for genes. And you may have several thousand of them. So the real challenge in analyzing that sort of data is that you've got very few observations, and you really want to try and extract as much information as you can out of them. And to make progress in that challenging situation, we often assume that the signal is sparse. So what this means is that there are only a few variables which contribute to the response that you're observing. You want to find out what those important variables are. The rest are unimportant. But many modern data sets don't really come in this sort of shape and size. And we're seeing data sets where actually both the number of observations and the number of variables may be very large and running into the millions or more. These are just two examples here which I'll talk about in this work. So in text analysis, your observations would be documents, and your variables will encode the frequency of words which are occurring in those documents. And you could add onto your variables frequency of pairs of words or triples of words, and then you can quickly end up with many millions of variables as you sort of look at higher order interactions of words. So the example that I'm going to be looking at here has around 4 million variables, and there are 16,000 documents. A similar sort of example is this URL reputation scoring. So here you've got many different URLs. You're trying to classify them as fraudulent or not fraudulent. And this data set this was the largest data set in the machine learning repository. You probably have heard of this machine learning repository on the internet. And at the time when we were doing this was the largest data set there. 3 million variables and 2 million observations. So, if you wanted to, say, apply a standard regression to, let's say, ridge regression to the text analysis problem, you might run into a little bit of trouble, and you'd certainly run into a lot of trouble if you tried to apply it directly to this URL example, especially if you wanted to do it quickly. So like I said, here, it's the size of the data which is giving you both computational and statistical challenges. So what can we do in this challenging situation? Well, in high-dimensional statistics, we assume that the signal is sparse, and we exploit that to make progress. And here, we often see sparsity in the design matrix. So that is that the matrix has many entries which are zero. And this is what I mean by sort of a sparse design matrix. So this is one observation from the URL example in what is known as SVM light format. So the one here is just saying, I guess, that this was a fraudulent URL. And what this is saying is for variable 4, the value is this 0.033195. And that's the value for variable 5. And this is the 2 million and something variable where the entry is 1, and all of the other numbers in that are 0. So you can see that the vast majority of the entries are actually 0, only this many are non-zero. So what approach are we going to take here? Well, seeing as the design matrix is so sparse, it seems as if there isn't really as much information contained in there. Although you've got a giant n by p matrix, which is a million or more maybe, because you've got so few non-zero entries, there isn't that much information contained in there, you might think. And so it would suggest that an approach based on dimension reduction, trying to reduce these many millions of variables down to a much more manageable number, might be a good approach. So we can try and create an n by L matrix S, and then try and perform regression on S rather than the giant matrix X. Oops. And the approach that we're going to take here is based on what I mentioned, this b-bit minwise hashing. So this is a technique which has its roots in computer science, and let me just describe sort of how it works. And like I said, it's not going to make much sense, and that's sort of the point, really. So Zi here is going to record the indices of the non-zero entries of the ith row of X. Okay, so just which variables are non-zero. And the way the method works is you generate L random permutations of 1 up to p. And then you just form this n by L matrix M in this way. So for the I-elfth entry, what you do is you apply each of your you apply permutation pi L to each member of Zi and then pick the minimum value. Okay, so it doesn't really make sense why you might be doing something like that, but we can agree that it's an easy enough task to perform computationally. It's very, very simple. Now, the next thing, actually general b-bit minwise hashing is a bit more complicated than this. So I'm just going to talk about 1-bit minwise hashing. And what you now do to this M matrix is you take the lowest bit of each entry of M and you form a new matrix. So basically, if the entry in the original M is odd, you put a 1, and if it's even, you put a 0. So you end up with this sort of a binary matrix. And now this binary matrix is an n by L matrix now, and supposedly you've chosen L to be smaller than P, and now what do? You just perform regression on this M1 matrix rather than the original X. And the rather amazing thing about this is that it actually works, and it does very well in these sorts of situations. And so we wanted to understand how this was happening, really. And in order to do this, we couldn't really study this directly. We sort of developed a variant of this method, which we call MRS mapping, and we've got some sort of theoretical results for that and why it tends to work, and what sorts of situations it works in. So let me describe what this MRS mapping is now. So we aim to create this compressed version of X, which will be S and an n by L matrix. So rather than looking at the lowest bits of the entries, we're actually going to use random signs. So this psi matrix is a matrix just consisting of IID random signs, each chosen with probability of half. And then you form two matrices, an n by L matrix H, and then finally the n by L matrix S. Now, you don't need to understand, or you don't need to really picture what's going on here, but the important thing to realize is that these are easy tasks to perform here. So all that's happening here is you're picking a minimum of permutations evaluated at all the different indices in Zi, and this is just an indexing operation here that's happening, and you're finally ending up with this S. So it's a simple operation. The computational cost is just L times the number of non-zero entries in X. So if you compare this to something like principal components analysis, that will involve all sorts of complicated iterations and things if you want to do an SVD decomposition or something, and that may well take far too long on data of this size, whereas this is almost the best that you can hope for. You're doing a single operation for each non-zero entry in your matrix X. The other thing to notice is that the rows of X are being processed individually. You don't need to load the whole thing up in memory, so it's got a very low memory footprint. And you can do all these rows in parallel as well if you wish. Now, for b-bit minwise hashing, actually, it didn't take account of the value of the entries in X, the numerical value of the entries. It just took account of whether they were non-zero or not. So actually, that can only be used for binary data. Here, we do incorporate the value of X here, although it's not clear how this makes sense, really. But this can be used with real valued entries, a design matrix with real valued entries. And the other advantage is that it also allows for variable importance measures to be calculated. So like I said, it's not going, I mean, there's no sort of intuitive understanding to be gained from this, really. You actually have to get down to the maths, and if I had a blackboard, I could show you some things maybe, but let's just move on to the theoretical results then. So we'll assume a linear model. So we've got an intercept term, the main effects, and here's some random noise, and the random noise has mean, zero, variance, sigma squared, and the different components of the noise are uncorrelated. Okay, simple enough. And we could add some sort of structural error here so that it's an approximately linear model, but I won't do that here. Without loss of generality, we assume that the column sums of X are zero. And what we'll arrive at are bounds on the mean squared prediction error. So basically, how well is this method doing in prediction? Okay, so we're going to let Q be the maximum number of non-zero entries across all rows of X. Actually, it doesn't need to be quite the maximum value. It's more like the average number of non-zero values, but leave it as the maximum for now. And we'll assume that all of the entries in X are bounded by 1. Then we get the following kind of result. So let's look at this L star to start off with. This is sort of, think of it as the optimal choice of L. So L was the dimension of the mapping. So we're going down from P down to L, and this L star is the L which is minimizing this upper bound on the prediction error. So it features here. So 2 is just a constant. We think of this thing as just a constant. The interesting part is really this bit here. And what's interesting is that P isn't featuring directly here at all. We just have Q, and P is only featuring implicitly through the L2 norm of beta star. So it's really the number of non-zero entries which matters, whereas if you were to apply ordinary least squares or something, you end up with P coming into the prediction error. You'll get P over N straight away. The other thing is here we have a 1 over root n rather than a 1 over n, which you'd expect, because we're looking at squared prediction error. So you would expect a 1 over n. The reason that this 1 over root n is coming in is because we're not making any assumptions on the design matrix. Typically, in order to get the fast rate of 1 over n, you need some sort of extra assumptions. But this is still an interesting enough result, I think. So you can play around with this and see sort of what implications it has. So if the size of the signal is fixed and the columns of X are roughly independent, then you're getting consistency provided P over N goes to 0, which is what you would get if you were doing ordinary least squares to start off with. But potentially you're getting a computational advantage here because you're going from P down to perhaps something smaller. Things are better if the signal is partially replicated in groups of variables, and then if you've got B groups of variables, you only need P over B, and that divided by N to go to 0, which is quite nice. And, and there's a very similar result for ridge regression. So this was with applying ordinary least squares to S. You can also apply ridge regression, and you get essentially the same result. And a similar result holds for logistic regression. Now here's the really interesting thing about this. We started out with our big matrix X, we compressed it down to something, a smaller matrix, and we think we must have lost some information in that compression. And we have obviously lost some information. But the really peculiar thing is that applying just a linear regression on this reduced matrix allows you to fit interactions in the bigger matrix. It's a really sort of surprising thing. And it's a particular form of interaction model, and this is the form that it takes. So here you've got the main effects, and this is the interaction part. And this is sort of a tensor product of the original variables and the sparsity pattern of the variables. So if your X were a binary matrix to start off with, then this would just include all interactions between variables. And now if we assume the linear model from before but replace the signal x beta star with f star here, then the previous results hold if we just replace the L2 norm of beta with this quantity here, which looks a little bit nasty, but this is just the main effects term from before, so this is the equivalent of that. And here, if we assume there are a fixed number of interactions of fixed size, then this part here is just a constant, and this whole thing here is of order root q. So if we've got a fixed number of main effects, we can think of the whole thing as being of order root q. And the sort of result that we get then is exactly the same as before, but with this quantity in here. And like I said, if we've got a fixed number of interaction in main effects terms of fixed size, this bit here is of order q, and then we get consistency provided q squared over n goes to 0. And if we were to just apply ordinary least squares to an expanded version of the original data to include all interactions, we need p squared over n to go to 0. So you're getting a phenomenal improvement, because q may well be something like 1,000th of p. Okay, I'll skip this variable importance part, I think, due to time. But this is an interesting extension. So this compressed design matrix S was formed in a random fashion. We had random permutations and we had random signs. So you can repeat the whole process and get another matrix S. And then you can regress on that and get another sort of prediction. And you can repeat this B times and average over the different predictions that you get in the similar spirit to bagging. And this turns out to do very well empirically. So we don't have a result for how well that does or why that does so well, but it really does do quite well. Okay, so I'll just quickly mention the real data examples, which I talked about at the beginning. So this text analysis was to do with, the documents in this text analysis were financial reports, and the aim here was to predict the volatility of the sort of the underlying stock, which corresponded to the particular financial report in the year after the report came out. So we used, in this regression we used various targets. The volatility after the report was released, and a linear and some artificial responses of a linear model and a nonlinear model, and we compare with random projections. With the original data, MRS mapping is blue, random projections, MRS mapping is red and random projections is blue. There's not really much difference here. This curve is giving the correlation between the prediction and the actual response. So high is good. And as you go along this curve, L is varying from 0 to 250. So we've gone down from 4 million predictive variables to 250 at the top there. And they're both these methods are doing quite well. For the linear model, again, both methods perform similarly. As soon as you include interactions, you see that this MRS mapping is doing much better. So it's really quite geared towards modeling interactions, it seems. And for the URL identification example, so in order to compare MRS mapping with just applying ridge regression or the lasso to the original data, we split the 2 million observations into consecutive days, because the data were collected over a number of days. And so this gave us several data sets with N is 20,000 and P is 100,000. And these are sort of the comparisons that you get. This is with B equals 1, so the original method. Here we're averaging over 20 different realizations of this S matrix. And and the dimension L is at the bottom here. So here we're going up to 1600, here we're going up to 400, and we're doing as well as the lasso applied to the original data, and the lasso here is being applied on the 100,000 predicted variable. So obviously, we're getting huge computational improvements there. And actually, you get a pretty big improvement if you're using ridge regression. So ridge regression on the original data is sort of up here with a much higher misclassification error, and with, well, after doing this compression and performing regression on the compressed matrix, you're doing much better in terms of misclassification error. Yeah, and that's sort of I guess I'm out of time, but yeah, that's the end of the talk. Thanks for listening.
Thank you.